Time series analysis. So previously we had learned something called the multiple linear regression, right? Now previously we had learned something called the multiple linear regression, right? In multiple linear regression, how it works is y is dependent on multiple independent variables. So y is the dependent variable which is dependent on multiple independent variables. Let's say a1 x1 is the first independent variable, then a2 x2 is the second independent variable. Like this, let's say there are n independent variables on which y is dependent, right? This is how multiple linear regression worked. Now friends, these were certain cross-sectional values or fundamental values in terms of economics. For example, let's say if y represents the stock's price, then x1 might be return on equity, x2 might be the experience of the managers, right? Like this. These are fundamental factors. These are not time sequence factors, for example. Now, if you go to Google and search, let's say, XYZ share price. If you search, let's say, XYZ share price, you'll come up with something like this. There will be a vertical axis where the prices will be plotted, and there is a horizontal axis where the time will be plotted, right? Let's say 1 month, 3 months, 6 month, 5 year, 10 year, like that, right? And a curve like this will be visible to you. Something like this, right? Now friends, this kind of a curve which is plotted against time. So here P is behaving as if it is varying with respect to time. This kind of a format of plotting is called a time series format. This kind of a plotting format is called a time series format. Time series. Right friends? This is called a time series. Now, time series can be represented in multiple ways. Let us take two basic examples. The first kind of model that we'll discuss is the linear trend model. So linear trend model, how does it look like? Basically, this is very similar to a linear regression model, friends. Here, the dependent variable y is dependent linearly on time. That is, y is equal to b0, b1 multiplied by time period plus, let's say, some error. Okay, b0 is the intercept. That is the value of y when t is equal to 0, and b1 is the slope. That is, with every change in t, the degree to which y changes, the extent to which y changes. The higher the slope, the higher the extent of change with every change of t, right? And the error obviously is that part of y which is not explained either by the intercept or by the slope or by the time period, right? So we are through with this. We have learned something like this in linear regression also. Here the only thing is the independent variable is time or the time period. Therefore, for t is equal to 0, y predicted or y hat is equal to b0, right? Because t is equal to 0. Then at t is equal to 1, y predicted is equal to b0 plus b1 because t is equal to 1. For the second time period 2, y predicted is equal to b0 plus 2 into b1 because t is equal to 2. Like this it goes on, right? This is how the linear trend model is represented, and this is the simplest form of model you can say of a time series. The second model we'll look at is a log linear trend model. Let's see how that looks like. Let's say the dependent variable y varies exponentially with respect to time. So y is equal to e to the power b0 plus b1 into t. This is, let's say, the equation. Okay. If we just rearrange the equation a little bit, this becomes natural log of y is equal to b0 plus b1 multiplied by t. This is called a log linear model. Why? This side it is logged and this side it is same as linear. So this is called a log linear model. Similar to the previous one, we can find out each of the values for each of the time periods, right? B0 is the intercept, I, let's say, we call it. B1 is the slope, right? Just to make sure that we know the concepts of intercept and slope, let me again revise those concepts. Let's say the vertical axis is representing y and the horizontal is t, right? Now we have two regression lines. One is like this and the other is like this. Now let's say the green one is line A and the red one is line B. Which one has a higher slope, friends? Obviously line B. That means B1 for B is greater than B1 for A. That is, the slope is higher. That is, for every change in T, the change in Y is higher for B. Right? If you want to test it or verify it pictorically, let's say the time changes from this point to this point. Now, if you measure the change of Y was here, then it went here, right? For line A, this is the change. This is the change in Y or del Y for A. And for B, what was the change? The previous position was here and the ultimate position was somewhere here. So the total change is this much, del YB. Now you can visibly see that del YB is greater than del YA. So the slope defines with every unit change of time what is the change or what is the extent of change, what is the magnitude of change of the dependent variable or Y. So we have understood what is slope, right? What is B1? We have understood. Now what is the intercept, friends? You can see in line A, at t is equal to 0, the value of Y is here, right? For line B, at t is equal to 0, the value of Y is here. So the Y being predicted for line B at t is equal to 0 is less than the Y predicted for A at t is equal to 0, which means the intercept for A is greater than intercept for B. Again, let's check it once more. This is A, intercept is this much. This is B, intercept is this much. Which one is more, friends? Obviously, B0 for A is more and B0 for B is less. So, intercept of A is more than the intercept of B. Intercept is what? The value of Y when the independent variable or time is equal to 0. This is the value of the intercept or B0. Now let's move on with our discussion, friends. When is a log linear model used, friends? So let's say a database is working like this. This is, let's say, the data. Now you are trying to fit a linear model to it. You try fitting this one. Does it work? No, right? Not the best fit. You try fitting this one. Well, it works for the higher results, but it fails to work for the lower results. So this one also doesn't work, right? So what do we do in this case, friends? Clearly, if we draw a line like this, it seems to work better. And this is nothing but an exponential equation, right? So an exponential equation means y is equal to e to the power b0 plus b1t, right? Now you do not want to use the exponential equation. You do not want to use it. You want to convert this database into something linear. So what do? You rearrange the equation. You rearrange this equation to something like this. So this becomes natural log of y is equal to b0 b1 to the power t, right? So in this database, the vertical axis is y and the horizontal is t. Now you make a change. What change? You change it to natural log of y. then how does the database become, friends? This becomes something like this. When you take vertical axis as the natural log of y instead of y only, then the line becomes like a linear line. This one. Now the regression is much more fitted for a linear equation. So your desire for using a linear regression also is fulfilled, and the data is also not, and the data fit or the regression fit is also good, right? So this is when you are trying to use a log linear model. That is when you have a exponential kind of a pattern when you are using the simple data y. What you do is you change it to natural log of y, and the data behaves like a linear data only. So that is what we call a log linear model, friends. Testing for serial correlation for trend models. So friend, trend models means y varies with time, right? Y is a function of time, nothing else but the time period. This is the simplest kind of time series model that we have discussed already in the form of linear models and log linear models. Now friends, we are here to test for serial correlation errors in a time series trend model. Okay, so how do we measure that? Now friends, there is a test statistic called Durbin-Watson statistic. Now the value of Durbin-Watson statistic ranges from 0 to 4 approximately. Okay, a value, let's say around 1.5 to 2.5 is considered okay. That means here there is no major serial correlation. No major serial correlation. But let's say if the value is 0.5, that is significantly less than 2, then this means positive serial correlation. And if the value is, let's say 3.5, that is significantly above 2, the implication is negative serial correlation. That is significant amount of negative serial correlation. So 1.5 to 2.5 or a mean value of 2 is ideal for a Durbin-Watson statistic value. If it becomes far less, it means positive serial correlation. If it becomes far more, it means negative serial correlation. So this is how we test for serial correlation in a trend analysis. Now friends, we'll move into a little more complicated version of time series, which is called the autoregressive model. Let's see what that is. So friends, in trend analysis, what happened was, we wrote something like this. Y is equal to B0 plus B1 multiplied by T plus some error, right? So Y was a function of time period. This was a trend model, friends. So what is the autoregressive model, friends? Basically, it is nothing but the current value yt is a value derived from one of its previous values. So let's say it is derived from its immediate previous value. So how the equation will be? Yt is equal to b0 plus b1 into yt minus 1. That is the value of y at just the previous period, plus obviously some error. So in this equation, yt, that is the y at current time, let's say t is equal to t, is a value which is a function of its previous value, previous period's value, yt minus 1. This is an autoregressive model, and more specifically, an autoregressive model of order 1, AR1. Why 1, friends? Because y is derived from its immediate previous value. So yt is a function of yt minus 1. That is why it is called a AR1. So this is a first order autoregressive model, right? Now what is the second order autoregressive model, friends? This is given by something like this. Yt is equal to b0 plus b1 yt minus 1 plus b2 yt minus 2 plus error. Let's call this error 1, error 2. Okay. This is called the second order autoregressive model, or AR2. Now we can generalize this. Yt is equal to b0 b1 yt minus 1 b2 yt minus 2 dot dot bp yt minus p plus some error. This is called a pth order autoregressive model. Now friends, for an autoregression model to be valid, it has to be covariance stationary. Now what do we mean by covariance stationary? Basically 3 conditions if fulfilled, the autoregressive model can be called covariance stationary. What are those 3 conditions? Number 1, the expected value of whatever we are measuring, let's say expected value of x or y, has to be constant, k, where k is a constant. Right? Across time periods, if this k keeps on changing a lot, then this cannot be called covariance stationary. Number 2 is covariance. The covariance of this variable at a certain lag, let's say xt minus s, the covariance between these two has to be constant. Let's give this a value called mu, where mu is a constant. Again, if this mu value changes with respect to time zones, then we cannot call the AR model, autoregressive model, to be a covariance stationary model. The third point, the mean value of x has to be constant. Let's give it value lambda, where lambda is constant. So the mean has to be constant, the covariance has to be constant, the expected value of x also has to be constant. Now the third point is the variance of x has to be constant across time zones. Variance of x has to be constant. So the variance of x has to be constant across time, covariance has to be constant across time at a certain lag, and the expected value of the variable also has to be constant across time zones. These 3 if simultaneously available, then only we can say that the autoregressive model is covariance stationary. Right? If any of these do not satisfy, then what will happen? Then the slope will become biased. The B1 will become biased. And the output estimates will become spurious or unreliable, right? So we will say that the AR has become invalid and we will be not able to do any hypothesis tests. So this is going to be the consequence if the covariance stationarity condition is not fulfilled by an autoregressive model. Now, how do we test for an autoregressive model covariance stationarity? Unfortunately, Durbin-Watson model is not valid for autoregressive models. So how do we do that? We do that through autocorrelation tests of errors. Let's see how we do that. So friends, let's say we are testing for serial correlation or autocorrelation at a lag of t minus s, right? So t with respect to t minus s we are trying to test. How do we test that? So let's say we are trying to measure the serial correlation of an autoregressive model at lag of s time periods. So we are comparing the variable at t with respect to the variable value at t minus s and trying to understand whether serial correlation exists or not. So how do we do that? So first we estimate the value of the variable x at time t minus s. Xt minus s is equal to, let's say, b0 b1 x t minus s minus 1 plus b2 x t minus s minus 2. This equation lag till s periods, right? So b s x t minus 2s plus the error for the variable x t minus s. So this is the first equation that we develop. The second equation is we try to estimate the value of xt. Xt is equal to b0 plus b1 xt minus 1 plus b2 xt minus 2 plus bs xt minus s plus error for the variable equation of xt. Now we have these two error values, friends. Error t minus s, error t. Now we do a correlation test for these two error values, friends. How do we do that? Correlation t minus s is equal to expected values of error t minus s minus expected value of error. Now in a time series, the expected value of error is 0. This expression multiplied by error for t minus expected value of error, which is again 0. This entire thing divided by the variance of the error value. Variance means standard deviation square, right? So here we have written here in place of variance we have written phi, right? Let me change the value here. Let me change the symbol here. It is basically sigma square. Now we are good, friends. So this is the correlation value, friends. Now how do we decide whether autocorrelation exists or not? What we do is, let's say there are 100 time periods in the model, right? There are 100 time periods. What we do is, we divide this correlation by root over of 100 and check the value of this. So if this value is more or less equal to 0, that means there is no serial correlation or autocorrelation. So in general terms, let's say if there are t time periods, capital T time periods, then we divide this correlation value sigma t minus s, rho t minus s by root over of capital T, and if it is more or less equal to 0 or nearby 0, that means there is no serial correlation or autocorrelation at lag of s, at the order of s. So this is the litmus test, friends. The value has to be nearby 0 or exactly equal to 0 or nearby 0 for there to be no autocorrelation or serial correlation. Now friends, the obvious question that arises is, how much different from 0? So what value or how much different value from 0 is different enough for us to consider that whether serial correlation exists or not, right? So let's say there is a model which has 4 lags. That is a 4th order autoregressive model. So xt is equal to b0, b1 xt minus 1, b2 xt minus 2, b3 x3 t minus 3, and b4 xt minus 4. So we are using 4 lag variables to describe the variable itself. Okay, so we write it t minus 4, the error also. Now, when we measure, let's say when we measure the autocorrelation or the correlation at t minus 1 divided by, let's say the number of observations is 200. So we keep it root over of 200. This value comes to be 0.57. Similarly, for t minus 2 root over of 200, this value comes to be 0.25. Similarly, for the other two variables, it comes to be 0.7 and 1.1, right? 1.1. So these are the values, right? Now, how do you know which? These are all very near to 0, right? These are all sufficiently near to 0. So how do we know which correlation is valid and which one is invalid? That is, which one does not have autocorrelation or serial correlation and which one has autocorrelation or serial correlation? We have a way to do that, friends. Here there are 5 parameters: B0, B1, B2, B3, B4. There are 5 parameters and the number of observations is 200. So we do one thing, we try to find out the t statistic for 5 parameters and 200 observations. Let's say the critical value of t is 0.98. So I have not calculated the exact value, friends. This is just I am using it for this example. This may not be the correct value of t in actual t tables, but I am just taking it as a value so that we can understand this example. Okay. So let's say the value, critical value is 0.98, right? Now compare this critical value with these values, friends. These 4 values. So this one is less, so this is good to go. So at t minus 1 there is no autocorrelation. At t minus 2 also there is no autocorrelation because this is less than the critical value 0.25. At t minus 3 also there is no autocorrelation. Only at t minus 4 we have the value greater than the critical value. So this one has an autocorrelation. There is autocorrelation or serial correlation here, right? At t minus 4. So the rest of the 3 observations are good to go, but the last observation, obviously at t minus 4 lag we are finding some autocorrelation. So the model at t minus 4 order is invalid. Okay. So what we have done is we have just compared the critical value with the value that is being calculated and try to understand whether the value is exceeding the critical value or not. If the value is not exceeding the critical value, obviously there is no autocorrelation. If it is exceeding the critical value, there is autocorrelation. It's as simple as that, friends. Now, friends, we will understand how the performance of an autoregressive model is measured. So, friends, there is something called root mean squared error or RMSE, which we use as a metric for performance for autoregressive models. So, let's say for the same kind of evaluation, we are using a AR1 model and a AR2 model. That is a second order autoregressive model and a first order autoregressive model. And this one, the AR1 model gives a RMSE of 1.25 and the AR2 model gives an RMSE of 1.7. So the root mean squared of the error is more in case of the AR2 model. So performance is better in case of AR1 model. This is a less error, right? Error less means performance is more. So we select AR1 instead of AR2. Now, friends, we will look at one more property of autoregressive models, which is called mean reversion. So mean reversion basically means, let's take the example of a stock price. For example, let's say the price was moving like this and some fundamental changes happened and the values now are expected to move like this. So till this point it was growing and from this point onwards it's expected to not grow, and not only not grow, it's expected to degrow. So this is the price of the stock, the vertical axis, and this is the time. So if we consider this to be an AR1 model, how do we represent this, friends? This point, let's call it the point M or the point of mean reversion. So how do we predict at what point this mean reversion will occur, friends? Logically speaking, at whatever point this happens, the phenomenon that happens at point M is basically this. PT becomes equal to PT plus 1. First the values become equal, right? Because there is a flattening of the value here. Here there is a flattening happening. So if the flattening is happening, at this point Pt is equal to Pt minus 1 at point M, right? So from this equation we can predict at what value the mean reversion might occur for this time series, right? So Pt is equal to, we have said this is an AR1 model, so this is going to be B0 plus B1 Pt. If we rearrange this, Pt is equal to B0 by 1 minus P1. So at this level, the mean reversion is predicted to happen for an AR1 time series model. We can generalize this for any variable xt of AR1 model. The mean reversion is predicted to be coming at P0 by 1 minus P1. Right, friends? So this is the value prediction. If somebody asks you that this is an AR1 model, the equation goes like this: xt is equal to B0 plus B1 xt minus 1. What is the value at which the mean reversion will happen? Tell us the value. Tell us the value. What you will do? You just rearrange this equation and replace xt minus 1 with xt and say that it will happen at xt is equal to B0 by 1 minus P1. Obviously B0 and B1 should be given. B0 and B1 should be given, and by measuring this you can predict the mean reversion point. It's as simple as that, friends. Instability of AR model parameters. Parameters means we are talking about B0, B1, B2, etc., etc. These coefficients and intercept. We are talking about the parameters. So why are the parameters unstable, friends? So specifically being a time series, what happens is many a times there are regime changes which influence the regression model itself. Let's say you're trying to plot the GDP numbers of USA with respect to last 50 years of time. So the vertical axis contains the GDP and the horizontal axis contains the years, that is the timelines, 70 to 80, 80 to 90, then 2000, 2010 and 20 onwards. Let's say the GDP numbers look something like this. Now friends, there is a problem in this data. This period of 70 to 80 was a period of great changes and high interest rates. There was complete decoupling from the gold standard, and the interest rates were soaring high in these periods, which is not at all similar to, let's say, period between 2000 to 2010. Here, the rates were very low, the interest rates were almost zero, and the fiat currency system had stabilized. There was a dot-com crash in 2000 which had brought about many economic changes. So these two periods are completely different, right? And again, these two periods were completely different from the period of 2010 to 20. Here the quantitative easing was happening full-fledged without that much impact on growth. The banks have been reorganized, the regulations had been reorganized of the financial systems because of the financial crash of 2010. So all these fundamental factors were different. Now it might so happen that if you try to draw a regression line, you will find that the errors are showing autocorrelation. These are not the exact GDP plots that I am doing here. I'm just trying to take an example. Here you can see the errors are biased on the downside. And here the errors are biased on the upside, especially 2000 to 2010, and then again some flattening is happening. I'm just guessing how it could be. But still it is upward biased in this entire regression. Now this regression is having autocorrelations in the error part. Obviously this is not a time series that we can bank on, right? So why this is happening, friends? Because there are different regimes being collated into one. Different regimes. That is a problem. Now let's say each of the years are taken as one period, right? And you draw a AR1 model, an AR2 model, a AR10 model, AR20 model, like that, right? And among them you see that the AR10 model is faring the best in terms of root mean squared errors and also in terms of checking the autocorrelations. So we will choose this one over AR1 model, AR2 model or AR20 model. So this impacts the parameters, friends. How? Because we have chosen a timeline of 50 years, we are finding that the parameters of AR10 model are giving the best regression. On the other hand, if we, for example, say regress for 20 years, we might find that the AR2 is giving the best regression. Or if you regress for a period of 10 years, last 10 years, what is the situation? Then we might find that the AR1 model is doing much better. And the parameter values will change for each of them. So the parameter values will depend on the entire universe of the time zone that you are choosing. And this makes the parameters unstable. We define this as the instability of the parameters of the ARP models. Now friends, we'll look at a special case of autoregressive model which is called a random walk. So friends, a random walk basically means a variable is moving randomly without any predictability towards it. So if this has to happen in terms of timeline, it can be represented like this. xt is equal to xt minus 1 plus an unpredictable error. An unpredictable error. Okay. And this is unpredictable and random both. Basically random, unpredictable, you can interchange the meanings of them. They mean basically the same thing. Unpredictable or random, right? So this is the equation of a random walk. Now, why am I calling this as a special case of autoregressor? So an autoregressive model looks like this. xt is equal to b0 plus b1 xt minus 1 plus error. This is an AR1 model. Now, let's make b0 is equal to 0 and b1 is equal to 1. This becomes exactly like the random walk equation. xt is equal to xt minus 1 multiplied by 1, which is the b1 plus the error. Right? So this is a case of special case of AR1 model, random walk. Here the expected value of xt is equal to xt minus 1. Right, friends? Why? Because the expected value of the error can be nothing but 0. Why? I'll tell you in a while. And the expected value of the variance is equal to sigma square. Similarly, expected value of the covariance is equal to 0. Now, because this is an autoregressive model, the required condition for an autoregressive model to be valid is that it has to be covariance stationary. So, is it being covariance stationary? Let us have a look at that. The expected value of xt is equal to, the best case can be xt minus 1 because expected value of error is equal to 0. It is equally probable that the error will be equal to minus 0.1 or plus 0.1. It is equally probable it will be equal to minus 0.2 or plus 0.2. It is equally possible that it will be equal to plus 1 or it is equally possible that it will be equal to minus 1 or plus 1. So if you sum them up, the expected value of this error becomes actually equal to 0. So the expected value of the error is 0, which means the expected value of xt is equal to xt minus 1. Now, if you want, AR model has to be covariance stationary. Now, the first condition of a covariance stationary model is fulfilled. If you take xt plus 1, the best guess will be xt, whose best guess is xt minus 1. So all these values, all the x values are basically constant. So all the expected x values are basically equal to a constant. So the first condition of covariance stationary is fulfilled. Now let us look at the second condition. What is the variance, friends? Let's say x1 is equal to 0. Therefore, x2 is equal to error of the equation x2. Now this implies that the variance of x2 is equal to variance of error 2. This is equal to sigma square. x3 is equal to x2 plus error for a random walk, right? This is equal to nothing but error 2 plus error 3. Now variance of x3 is equal to variance of error 2 plus variance of error 3, both of which are equal to sigma square. Therefore, this is equal to 2 into sigma square. Similarly, if you extend it, this becomes variance of xt is equal to t minus 1 multiplied by sigma square. This means the variance has no upper bound. Variance has no upper bound. It moves up as the t moves up, right? So this violates the covariance stationary condition. This violates the covariance stationary condition, right? Now let us also have a look at the covariance. Let's say we are looking at the covariance at a lag of s. So covariance of error at t and error at t minus s. This is equal to expected value of error at t minus estimated value of error, which is 0, multiplied by error t minus s minus 0. Now the expected value of error t and expected value of error t minus s both are equal to 0. Therefore, the covariance also becomes equal to 0. So these two conditions, covariance and expected value of xt, these two conditions are sort of fulfilled. So because one of the three conditions of being covariance stationary is being violated, the model is not following the covariance stationary rule. So how can we mitigate this problem, friends? Let's have a look at it. To make this model covariance stationary, what we do is something called first differencing. So we take out something called yt, which is equal to xt minus 1. This is nothing but xt minus 1 plus error minus xt minus 1, which is equal to nothing but error. So this is what the first differentiation looks like. Now this makes it covariance stationary. How so? First, the variance was violating in the previous equation, right? So let us check the variance here. Variance of yt, this is equal to variance of xt minus variance of xt minus 1. So this is equal to, from the previous equation, this will be t minus 1 into sigma square minus t minus 2 into sigma square, right? If you just simplify this, this becomes equal to sigma square. So the t variable is gone. Sigma square becomes a constant value, which is the variance of yt. So the variance part is gone. And the expected value of yt is nothing but 0, because expected value of error is nothing but 0. Now this is one factor for the model to be covariance stationary. We have checked this is okay. This was being violated previously. The second factor, here also we are okay. The third factor, the covariance. The covariance of, let's say, error t minus 1, error t minus s. This is equal to nothing but 0. We have spoken in the previous formula itself. It is given by expected value of error t minus 0 multiplied by error t minus s minus 0. So if these are all estimated values, et and et minus s are expected to be 0. So the entire value is equal to 0. So the covariance is 0. So all the three conditions are satisfied. This is finite and constant covariance. The variance is finite and constant, and the expected value of the variable is also finite and constant. One more thing, if you want to confirm the covariance stationarity, is the mean reversion point. So the mean reversion point for the non-first differentiated model looks something like this. Xt is equal to b0 by 1 minus b1, right? Here b1 is equal to 1 and b0 is equal to 0. So this entire value becomes 0 by 0, which is undefined. So the mean reversion point before first differencing is undefined. And what about yt? What about the mean reversion point after first differencing? Yt is equal to, again if you write b0 1 minus b1, here b0 is equal to 0 and b1 also is equal to 0, because we have seen here. So if you see the equation above, friends, here yt is equal to error t. So there is no b1 present. b1 is actually equal to 0. So here we can write yt is equal to 0 by 1 minus 0. This is equal to 0 by 1, or the value is 0. The mean reversion point predictably is 0 for a random walk. So we have a defined point of mean reversion. So this is another way which proves that yt is covariance stationary. So friends, what is a random walk with a drift? So we have learned that random walk is represented like this. Xt is equal to xt minus 1 plus error at t, right? Now here b1 is equal to 1 and b0 is equal to 0. Now if there has to be a drift, what has to change here? The thing that changes is the b0. The b0 becomes not equal to 0. So this equation transforms to xt is equal to b0 plus xt minus 1 plus the error. This is a random walk with a drift. Dickey-Fuller unit root test. This is a test of what factor, friends? It is a test of non-stationarity. Now what do we mean by this? So friends, the random walk equation we can write like this. Xt is equal to xt minus 1 plus the error, which is unpredictable, right? Now this is a special case of AR model, that is the autoregressive model, which is given by xt is equal to b0 plus b1 xt minus 1 plus the error. This is just a special case of autoregressive model or AR1 model. Now this model, AR1 model, has some limitations, friend. We cannot accept a model which has a b1 which is equal to or greater than 1. b1 cannot be equal to 1 or greater than 1. We only accept equations where b1 is less than 1. This is the only case where the non-stationarity condition is fulfilled. Now how do we test for it? Previously we have tested autocorrelation by the help of t statistics, right? We have measured the t critical values. We have measured the t critical values and compared it with the t stat to find out whether the value is significantly different for 0 or not, right? We have done this error autocorrelation thing. You can find in the previous section. But here, friends, this is not possible. The reason being, at b1 equal to 1, the equation becomes non-stationary. The equation itself becomes non-stationary. So autocorrelation measurements with the help of t statistics cannot be done here, right? So we have to do something else. What do we do? Here we use something called the Dickey-Fuller unit root test. What Dickey and Fuller did is they subtracted xt minus 1 from both the sides. So xt minus 1 is equal to b0 plus b1 minus 1 into xt minus 1, because we subtract xt minus 1 from both sides, this happens, plus the error term. Right? We'll just transform the equation a little bit. Now we call this yt is equal to b0 plus b1 minus 1. We call this g multiplied by xt minus 1 plus error. Now we test for this g. That is, the null hypothesis says that g is equal to 0. That is, b1 is equal to 1, which implies there is non-stationarity. Non-stationarity is there. And the alternative hypothesis naturally is g is less than 1, which means non-stationarity is not there. That is, the model is valid. Now, how do we test whether the g is equal to 0 or not? Obviously, there is something called t-statistic for Dickey-Fuller test. And the critical value of this is greater than the absolute values of the t-critical values in normal t-stats tests. Right? So the absolute values are greater. So we measure the t-statistic with respect to g and compare it with the Dickey-Fuller t-stat critical values, and then if the critical value is greater, then we say the null hypothesis is rejected. So H0 is rejected if t-stat for Dickey-Fuller test is less than the t-critical for Dickey-Fuller test. So this is how the Dickey-Fuller unit root test is done for non-stationary difference. And this is obviously with respect to AR models, specifically AR1 models.